Hello, everyone. I'm Deep Medhi. I'm the organizer of SKC Science and Technology webinar. And today we have the pleasure of having Frank Wuerthwein as the speaker on this fireside chat format. Frank is actually the executive director of Open Science Grid and the interim director of the San Diego Supercomputer Center. As if that's not enough for him to do, he's also professor of physics at University of California at San Diego. He looks at big science with big instruments and how, many things in big sciences we can actually learn from having the instrumentation, especially from a computing point of view, at the intersection of physics and computer science. So with that intro, I'll let Frank chat and talk through it. And he has a few slides. And again, as I said, it's a fireside chat format. So what we'll do is that as needed, I'm going to stop and ask him question, and then we'll go from there. Okay, Frank?
Yep.
Okay, let's go.
So the abstract of this talk is I will provide an overview of two global science drivers: gravitational wave observatories and the ice-cube neutrino observatory. And I will elucidate some common patterns in the architecture of the global computing infrastructure, but most of this talk is actually about the science. I picked those two science topics. Because they have a common theme. But before I go there, let me say one thing about myself. I'm what we call at the San Diego Supercomputer Center a pi person. A pi person is somebody who has two legs firmly planted in two different disciplines, where one of the disciplines is some domain science. In my case, this is experimental particle physics. And the other discipline is cyber infrastructure, software computing, something like this. And in my case, this is globally distributed computing. And then the bar across on the pi is we think of as the research. So the research of a pi person spans all the way from totally in one domain where to totally in the other domain and everything in between.
I see.
And the San Diego Supercomputer Center prides itself on having lots of pi people. And that is what makes the center productive and able to translate innovation into practice. That's what we do. So
if you do anything with pi, does it also mean you have some irrational thoughts because of pi being an irrational number? So
less so, but I had never thought of that angle.
Okay, all right. Okay.
It's basically it's a cute play on the visuals.
Okay.
And the fact that it is obviously something that has to do with math, science, and technology.
Of course.
But, the rationality versus the irrationality, interesting twist.
Okay. All right. Okay.
So let me start with the science. So the connecting tissue between these two large-scale instruments is the notion of multidimensional astrophysics. So what I'm showing here is a view graph that shows the energy of photons in EV versus the distance that they travel through the universe. And what you see that there is an area all in black here where the universe is opaque. In other words, if you have photons above about 10 to the 11 EV, then they will not reach you if the distance is anywhere further than an 10 to the minus 2 megaparsec or so. So in essence, this area here, in this area, the universe is completely opaque to light, and the only messengers, as we call them, basically the only kind of information that still reaches us for energies in this range and distances in this range are either gravitational waves or neutrinos. And the holy grail of multidimensional astrophysics is to observe the most violent events in the universe and do so by virtue of observing either gravitational waves or neutrinos, because the observatories that do so cover the full sky. And once you see something, you immediately analyze where it's coming from. And then given that all satellites and ground-based telescopes, in other words, all light-based instruments anywhere across the entire spectrum of frequencies of light, they're all essentially pointing devices, meaning they have a very small angle of view. And if you don't point them directly at something, you can't observe it. So gravitational waves and neutrinos will detect something that's very violent and otherwise not visible because it's in this area. And then they will send a signal to the telescopes and satellites that humanity operates and say, look there. And then these telescopes get to decide and satellites get to decide whether they want to, because it's interesting, because they want to participate in this kind of science. And I will show you examples where this has actually happened, and therefore groundbreaking new observations have been made.
So I have two questions right now, Frank. One is that define what you mean by violent. You know, what is the context of what you consider violent?
I use violent simply because it's the largest possible energies that anybody has observed phenomena in. So, if you think of the energy scale here, if you're at low energies anywhere here, then you can study things based on light, and we have a gazillion measurements of all kinds of phenomena in the radio wave, the microwave, the infrared, the X-rays, the gamma rays, all over the map.
Yeah, the things we know about.
In this really, really high energy region, where you have the most violent phenomena, meaning the highest energy in the phenomena that anybody's ever seen in the universe, you can't use light because it wouldn't get to us.
I see.
And therefore, you have to use gravitational waves or neutrinos, because those two types of phenomena will actually reach us because they don't interact at all electromagnetically. They interact very, very weakly for the neutrinos and even weaker for the gravitational waves.
The second question I have is that when you have the term multi-messenger, I presume that's what you mean about getting it through different ways or messaging ways to be able to get that information, right? Because you cannot get the information as you will get with normal energy, that, one way, basically. Did I get that right?
Correct. Yes, exactly. So a messenger is the type of radiation, if you wish, that is sent by the violent phenomenon. And in principle, there are phenomena where you would expect to see all three of them: light, gravitational waves, and neutrinos. But the only thing that's ever been observed have been either gravitational waves plus light or a neutrino plus light. And I'll talk about that in this talk. And so multi-messenger today means typically a gravitational wave plus radio plus various different kinds of electromagnetic radiation, meaning different lights at different frequency, or a neutrino plus light at all kinds of different frequencies. That's typically what's been done so far. And even there's actually an astoundingly few examples. And the first time anything like this has ever been done was in 2015. And I'll talk about that too.
So it is very, very
it's a very new field.
Very new field. Very
it's a
exciting.
very, very new field.
Okay.
Okay, I'm good for now. So then let me start by talking about gravitational waves and the kind of things that people want to observe with gravitational waves. And there's really four types of phenomena. One of them has been observed. That's the coalescing binary systems, and the other three have never been seen. They're being searched for, but there's no actual observation of a gravitational wave that is in either a continuous source, a stochastic background, or a burst. there is a continuous source measurement indirectly from the spiraling in of a source that get the Nobel Prize. I want to say it was a Nobel Prize in the 90s or 2000s or thereabouts. I've forgotten now the exact time. So that was not a direct observation, but an indirect observation. So we know that these kinds of phenomena exist, but we don't have the sensitivity yet with the Gravitational Wave Authority to actually see it. And the ones that have been seen are coalescing binaries. What you should think of here, imagine two very, very heavy objects. They are building a binary system that circles around each other. And as they send off energy in form of waves, they spiral in ever closer, and then in the end collide. And that kind of thing gives a very specific signature. It's a chirp. It's literally something that starts out at a low frequency and ends at a high frequency. And that very characteristic chirp has been observed. And I'll talk about that in a second. So far, so good?
Good.
And so the first observation of a gravitational wave, the actual observation of the actual wave, was 2015. And this was on September 14th, 2015. And that was done with the LIGO Observatory. And I'll show you what LIGO is and how it works in the next few slides. And LIGO literally, in fact, it was during the commissioning run when they had just started data taking and hadn't even fully commissioned and understood the instrument yet, a incredibly strong gravitational wave passed by Earth that was well within the frequency band and the amplitude, or had enough amplitude to actually be observed by the detector. And it was detected on September 14, 2015. And this down here is the waveform that has been observed by the two observatories, the two detectors, blue being one of the two, red being the other. And you can see that they're totally consistent. And it was interpreted afterwards, when fully analyzed, it was interpreted as a binary black hole coalescence. And from the waveform, they could measure the mass of each black hole and the total mass of the combined object, and therefore infer the total amount of energy that was sent off in this collision. Given that black holes, the very nature that they're black holes means there is no radiation, no light sent off. So this one had no light attached to it. People immediately looked for the light from this possible collision and saw none. And the waveform, when carefully analyzed, also was consistent with a black hole collision rather than something else. And then 2 years later, in August 17, 2017, the first ever observation of a simultaneous observation of a gravitational wave plus, so another chirp, another binary inspiral. And you can see here the actual chirp. And another binary inspiral was observed. And this time, again, LIGO pointed in the sky where to look for the optical signal, and multiple satellites and ground-based telescope all looked in that direction, and multiple of them could actually see the signal also in the optical. And then when analyzed, it was concluded that this was a neutron star binary, so two neutron stars that inspiral. And given that they have a lot of not just mass, but also matter, this sent off both light across the entire frequency spectrum and gravity waves. And the gravity waves gave you a total energy release. And the light gave you sort of an indication of the lower frequencies part of the spectrum where it was visible because of in the higher frequencies, in the higher energy part of the spectrum, you couldn't see it because of the universe being opaque. Any questions so far?
Yeah, one question I have is that obviously the whole idea of the concept of gravitational wave, correct me if I'm wrong, goes back to Einstein talking about it almost
Correct.
100 years ago. And from 100 years ago, that concept to bring it to light of being able to detect it like this, a lot of work has obviously gone into it, just what sort of ways we can do it and how to do it. And as you'll probably talk about in a little bit, LIGO is one of those instruments that allowed to actually, capture and, what actually, this kind of gravitational wave that can happen because of something that happened in the universe, basically the pool, right?
Correct. And in fact, gravitational wave observatories is a particularly relevant topic for people in India because there's a large Indian investment into another observatory called LIGO India, with the lead institution is IUCAA near in Pune.
Okay.
And I'll talk a little bit more about that as we go through this.
Okay, very good. Thank you.
I've actually visited IUCAA because of my work with the LIGO computing.
Okay, I see. Okay, great.
And another one that is sort of really mind-boggling, if you look at these kinds of signals, take, for example, this here. This was a signal that the collision actually happened 1.3 billion years ago.
Right.
Then
right.
it traveled, the gravitational wave traveled throughout the universe for 1.3 billion years. And it passed Earth, and it left in the LIGO detector a signal that was just a few seconds or even a fraction of a second long. So it is an incredibly short signal of a wave passing by, and we only detect it because it happens to be for a very period of time in our sensitivity band where we can see it. It's sort of mind-boggling to think that something 1.3 billion years ago happened. It travels through a large part of the universe for seemingly forever, more than a billion years, and then we see it for a tiny amount of time.
It's almost like a matter of luck that you could catch it at that particular point when the instrument
exactly.
was
It's
being
actually
built.
a matter of we're exceedingly lucky that the instrument turned on right then, and we could immediately see something.
Yep.
Now,
so
I want to give a little bit of a
one more quick question before we go into this, which means that gravitational waves probably are continually coming through the universe, that we are obviously not detecting it because we don't have the instrument, or even the instrument LIGO might not be able to detect something because it doesn't have the precision to be able to detect it. Is that a fair assessment then, Frank?
Yes. In fact, if you think of this, if you think of a chip like this, LIGO is sensitive only over a certain frequency range, and it's only sensitive to a certain minimum amplitude. So if the signal doesn't land in the frequency range of LIGO or doesn't have enough of an amplitude, then LIGO will simply not see it.
Okay.
And when you look at all of these things here, the other three types of sources, there are clear predictions that those things will exist. It's just that we haven't seen any of them yet because we don't have we're either not sensitive to the right frequency range, or they don't have enough of an amplitude, meaning they're not close enough to us. Because if you think about something happening somewhere, and then a wave goes in all directions, spherically symmetric outwards, its amplitude decreases with distance, right? And so if we're not close enough, we won't even, or it is not violent enough, meaning energetic enough, we will not see it.
Okay, got it.
Does that make sense?
Sure.
So then let me talk a little bit about the physics for gravitational waves. I personally find this such a cool piece of physics that I can't resist the temptation talking about it, even though it's actually not my field. I teach this when I teach waves for introphysics. Basically, we have a sequence of physics for engineers at UCSD. When I teach waves, I set aside one lecture where typically the lecture before Thanksgiving or something like that, where I say, okay, fine, today I'm only going to talk about things that I find fun, but it's not going to be on any exam. And invariably, I talk about gravitational waves because I think this is such a cool topic.
Okay.
So you'll get some of this now, a few slides of this.
Okay.
So the easiest way to think about how a gravitational wave gets produced is that any mass that sits somewhere in space-time will bend space-time because of the very existence of the mass. In other words, there is Einstein's theory of gravitation predicts that there is a relationship between masses and the curvature of space-time, and the vicinity of any mass will lead to a bending of space-time. And then if you then imagine that you have this ball, which is a very heavy object, sitting inside space-time and therefore sort of bending space-time. Now imagine this ball explodes and all of the mass disappears. What would happen? The space-time that is bent would then oscillate up and down, just like when you drop a pebble into water. Am I making sense?
Yep. Sure.
And that fluctuation up and down would propagate outwards. And that's exactly a gravitational wave that one would observe. So
Nice.
The actual gravitational waves that are observed are slightly more complicated because you have two objects here that spiral inwardsly. Then when they get very close, they collide, they dissipate into one. So the two black holes merge into one black hole. That one black hole has a lot less mass. So mass suddenly disappears, turns into energy, and that energy gets dissipated with the wave outwards in all directions. And we see it 1.3 billion years later, passing through the universe where we happen to be situated. Does that make sense?
Very interesting.
It's pretty wild.
Right.
Now, the next thing that is very cool is that gravitational waves are actually very, very weird and peculiar. I don't know, you probably know that at light, electromagnetic waves, has the characteristics that it is polarized. So in other words, the electric and the magnetic field for light are at a right angle. And the amplitude is basically a shrinking and expanding of both of these simultaneously as you go through space. Now, for a gravitational wave, it is a quadrupole bending of sorts. What I mean by this, you can think of having the space-time being a sheet of cloth, and as a wave goes through space-time, you stretch it first in one direction, and then in the next half period, you stretch it in the other direction. So effectively, as a wave goes through the origin here, it would first stretch in X, and then it would stretch in Y. And so the entire space-time, meaning everything in space and time, stretches and shrinks as the wave passes. Can you wrap around your head around this?
Yep. Right.
So now, now what happens? Now I want to illustrate this in a two-dimensional. So imagine a wave passes a circular thing with lots of different masses. What you would see is that it would first constrict it this way and stretch it that way. Then a moment later, it would be a perfect circle. And then a moment later, it would stretch it this direction and squash it that direction. Right. That's effectively what the wave does as it passes. Now, how do you observe this? You observe this with something that's called a Michelson interferometer. A Michelson interferometer is an instrument that has a laser light, and it shines laser light on a half mirror. That laser light gets then split. Half of it goes this way, half of it goes that way. Here you have a mirror. Here you have a mirror. and then it reflects back. It reflects back, and they then get split again. Half of it reflects here, half of it goes through, and then here you put a detector, and the detector literally measures a superposition of the light that was reflected here and the light that was reflected here. And depending on how space was elongated or compressed, you will have created a phase difference between the light that reflected here and the light reflected here. And therefore, this superposition will see a minimum fringes. It will see basically a fringe pattern where you have a positive, a constructive interference and destructive interference. In other words, no light and light. And that phenomenon is observed in an incredibly precise detector. And this is sort of the basic principle of observation. You have a micro-interferometer with two very long arms, and I'll show you a picture in a second, with mirrors at the end, with a laser that is really, really strong to get a lot of power, and then a detector that can detect incredibly small phase differences between these two mirrors, so that you have an incredibly small difference in distances that you're measuring. Because what you're measuring when the wave goes by is that this gets squashed, this distance gets squashed, this distance gets elongated, and then a moment later they're the same, and a moment later this is squashed and this is elongated. And that pattern is the pattern that you ultimately see.
Okay, so which means that if it is exactly like circle in the middle, then they're going to match up because of the distance being same on the
correct,
x-axis versus, I'll call it x-axis, but vertical versus horizontal. Then you are not going to see any difference. Then you're going to see something right before that, because you're under like a more like an oval shape with the vertical oval, or right after that, because you're more like a flattened oval, basically. Correct? And then it's going to kind of repeat it in a sense. You're going to see it, not see it, see it, not see it, but continue like that. Okay,
and then it depends on how many wiggles of the waves do you actually see.
Exactly, correct.
As the thing passes through.
Very neat.
How long you can think of it, how long a wave packet, the original explosion or whatever the violent phenomena was, actually sent into space, how large a wave packet that is. You can, and then think, if you want to do this really properly mathematically, you do a Fourier transform of the wave packet in space, and then you get a frequency response, and then you have a certain frequency you can detect, others you can't, and therefore you end up with a frequency analysis of the sensitivity of the experiment.
Right.
And I think that's sort of maybe too much.
Yeah, right. Even for me, that's too much. So okay, but I got the hint. So yeah, but this picture is great. This is very, very useful because you get the simple idea across on what's going on. I do have one question.
It all lies in the fact that it all lies in the fact that the very nature of the wave is the stretching and squishing of space-time. Right, so the fact that it does this here makes this the perfect experiment to observe it.
What's the advantage of using the laser here in this particular case, in the context of gravitational wave?
Laser interferometry is the most precise way that we know how to measure distance differences. This is because if you think of the laser frequency, this is optical. In the optical, if you think of the laser frequency and the speed of light giving you the wavelength, and you can observe shifts smaller than the wavelength, and therefore have an incredibly precise instrument here. And I'm going to talk about this in a second when you actually see what these instruments look like. This is what this looks like in the real axis, meaning these are the actual instruments. This one is located in Hanford, Washington, and this one is located in Baton Rouge, Louisiana, or near there.
Okay.
And so in both cases, these instruments are built in the middle of nowhere because they are so incredibly sensitive that for this instrument in Louisiana, for example, they built it and then they realized that there was logging activity, meaning trees were felled kilometers away from the instrument. and they had trouble getting the sensitivity down because those falling trees on the ground would disturb the instrument.
Very
And so
interesting.
to give you a sense, the arm here is 4 kilometers in length. The mirror, this is the Michelson interferometer, right? The laser is somewhere here in this building. The far, so this mirror and that mirror, this distance here, this distance is 4 kilometers.
Got it.
Just to set the scale. The tunnel that this is in is literally man size and ultra high backroom. Because the laser beam is shot across 4 kilometers in this cavity and is not allowed to have any kind of disturbances. Therefore, you have absolute, incredibly good vacuum in here so that the light doesn't scatter off any atoms or molecules inside the cavity. So this is an unbelievable tour de force. If I remember correctly, the strain sensitivity, meaning the distance difference here, is 10 to the minus 19 meters.
Okay, wow.
It is the absolute most precise distance measurement that anybody on Earth has ever made in any way, shape, or form.
Okay, there's a question came up actually. How about the earthquakes? Does a small quake also affect
you
it?
cannot possibly, yes, you cannot possibly put this anywhere where you have significant seismic activity.
Okay. So the location is very important when you choose it. Okay.
Yes, the location is very important. In addition, I don't think I have I don't have a. There's actually, when I give this as a talk as a lecture, at lecture length, I have pictures of the actual instrument where the test masters sit and where the mirrors sit and so forth. And these mirrors, they are sitting on a seismic isolation stack. The first generation was on a passive seismic isolation stack. The current generation is actually active feedback seismic isolation, because even if you don't have earthquakes typically in this area, any kind of earth movement whatsoever, like I mentioned, a tree falling or a truck driving outside, would cause enough seismic activity, meaning earth movement, that you must isolate the entire instrument against that by putting it on specially designed seismic isolation equipment that is actually an active feedback. So the technical details of these kinds of instruments are just phenomenal, just unbelievable.
Okay.
And it is. Then the next thing is that this was chosen. These two locations were chosen such as to be in areas that are ideal for this kind of this quiet areas, but also far apart from each other, so that you can both do triangulation, meaning when you think about the Earth as a globe, and then a wave comes out of some direction, and you have these things lined up. You actually need 3 of these instruments to get a perfect location of the point in the sky. With 2 instruments only when the wave is particularly oriented do you get a decent location. And with 2 instruments, it's possible to completely miss it. Certain types of polarization of think of the wave basically does this and that, right? Now, this means there's an XY axis to it. And that XY axis has an orientation around the propagation, right? And depending on how that orientation is located with respect to the arm's location of the actual physical instrument, you end up either having a good position or a bad position location, pointing accuracy into the sky.
I see.
And the more instruments you have on the globe, the better is your location ability to locate.
I see. Okay.
Making any sense?
No, of course. Yeah, you have more precision in terms of being able to capture those things. So So you're saying that there's one, if I read your slide, there's one in Italy and then Japan and then one in India near Pune, you said, where it was built, or are they?
There's one in Italy that's been running for a while.
Mhm.
There's one in Japan that I think has its first run this year, and it may have gotten delayed because of COVID. I'm not 100% sure that it's actually run yet. So that the one in Japan is close to or doing science, and the one in India is being built, and I've forgotten where it is being built. It's not in Pune.
Okay.
The institution responsible is in Pune, meaning
Okay.
the lab that is responsible for building it. I believe it's somewhere in the middle of nowhere, somewhere in the south, but I
Okay.
don't remember where.
Okay. Very interesting. Okay.
And so you have this then, and this is the first observation, the 2015 observation, the first detection in 2015, led to the Nobel Prize in 2017 to these three fellows, and this is sort of the cleaned up view of what they observed.
Okay.
And LIGO has since seen dozens of waves. Basically, the name of the game for LIGO is you, over time, improve the strain sensitivity, meaning you improve the detection of the minimal distance difference in the interferometer that you can detect, and that is referred to as strain sensitivity. You can think of this: you improve your precision on seeing amplitude. And as you improve your precision on seeing amplitude, you can see further and further into the universe.
Right.
For the same original amplitude, the same amount of energy originally released, the further away it is, the fainter it becomes for us. And so what happens if you increase the sensitivity of the instrument by a factor 2, you actually increase the radius that you're sensitive to by a factor 8, because it goes like the radius cubed. So as a result of this, go ahead.
No. Which means that the instrument that is built right now almost seems not as precise as you would like, but hopefully less than next 10 to 20 years we'll even have a better instrumentation capability to do more and more gravitational waves being able to capture it, basically, because of that.
And exactly, and you can think of it as once you've seen the first one, you are virtually guaranteed that any improvement of the instrument from there onwards, you will see lots and lots more. Because you can think of it as you are sensitive to a volume in space, and as you improve the instrument, the volume in space that you are sensitive to for a given size phenomenon grows like the cube of the sensitivity. So a factor of 2 improvement gives a factor of 8 in radius. Gets a factor of 8 in volume, because it goes like the radius cube. Volume goes like the radius cube. If you, in essence, if you improve by a factor of 2 the sensitivity, that translates directly into radius that you can look. And given that volume goes radius cubed, you get 8 times more waves of this, if they happen of a certain the same strength than you got the first time around. Am I making any sense?
Yep. Got it. Yep.
And as you improve sensitivity, you are getting more sensitive. You will see more and more waves because your volume increases, and you'll be sensitive to smaller amplitudes closer by. So it sort of helps you double in a funny way. Effectively, LIGO, and that's why this is so exciting, this kind of science, because there's an explosion of discoveries or observations that you can then do science with, because you're collecting more and more of these phenomena. And now, where is the world going? This has become a global quest. In fact, LIGO has built a global collaboration, starting with a collaboration with and GEO 600, which is a very small experiment with not much sensitivity. Now we're adding in Kagra or they're adding in Kagra, and then the next one will be LIGO India. And so all of these instruments share their data and do simultaneous observations in order to maximize the science.
Okay.
And then the one thing that is worth pointing out, this program is going to run for another 10, 20 years. I don't remember the exact timeline. And then people are already talking about what's the next thing you can do. And the next thing that you can do is put these interferometers into space and actually have them put basically 3 interferometers that are arranged to build a triangle.
Correct.
And they're going into space, because in space you don't have seismic problems.
That's
you don't
correct.
have a lot of the disturbances that you have are gone. Of course, technically these are even more challenging to do, because you're now suddenly sending laser signals in space. But anyway, this is sort of where this is heading.
Okay, let me quickly ask a question about the space thing. Very intriguing. Let's say we can still build it. I mean, hopefully we can build it. We have built many things. So if we do that, obviously one thing that will still affect is the gravitational wave. It's coming in all the time. But it is possible that there might be other sort of potentially waves or some others, not seismic thing like that you see it on Earth, but some other sort of kind of a violent explosion somewhere that can also affect the instrument potential even in space. I mean, conceptually, is it possible?
I'm much less familiar with the work that's been done on the space-based stuff, but there are obvious challenges in space. Even such simple things as debris, right? There's all kinds of space junk that flies around.
That's right.
And you will have to figure out how to protect these instruments from getting hit by
an asteroid,
asteroids. And
right.
And so there's all kinds of
other
challenges.
Issues. Okay, got it. Okay,
that you have out there. And if you think about it, in important sensitivity, if you think about when you locate something on Earth, your frequency has a brick wall. Unfortunately, I took this out, this slide. They actually describe their sensitivity as a function in a 2-dimensional plane, where the y-axis is the sensitivity in strain, meaning position, and the x-axis is the frequency. And at low frequency, your sensitivity is basically, it's a brick wall. You can't observe anything because of seismic activity, because the Earth shakes very gradually. And at high frequency, you have all kinds of shock noise and quantum noise and all kinds of effects like that, and that limits you at high frequency. And as you're going into space, the low frequency limit completely disappears, so you can go down to much lower frequency, and therefore can see a completely different type of phenomena of gravitational waves that you will never see on Earth. Am I making sense?
Right. That's true. I mean, I did ask about the space debris. I mean, we talked about it, but another part of the question somebody asked was that any other violent radiation that might affect the space instruments, I guess.
Typically, that sort of thing we know how to shield against, so that I'm not so worried.
I see.
You just have to build the thing accordingly.
Okay, got it.
There are obvious challenges, technical challenges of how do you shield against radiation from the sun, and where do you exactly locate it, and does it make sense to have it always in the shadow of the sun, behind the Earth, so that it actually moves as the sun moves, and all of those kinds of things. I have no idea. I haven't actually. They're all questions that you can ask yourself.
Sure.
I know that people are working on this, but I actually haven't paid attention. So I don't know anything. I was a Caltech postdoc when the first LIGO was constructed.
Okay.
And so I know a lot more about the LIGO instrument simply by being there when it was built
Aha, of
at
course.
Caltech.
What
And
an
so,
experience. Yeah.
in fact, this guy here, Barry Barish, he hired me as he's a particle physics. He comes from particle physics.
Okay.
He's a physicist physics professor at Caltech, and he originally hired me for particle physics. And then once I was at Caltech, and given that I was his postdoc, he sort of offered me if I wanted to switch to LIGO, I could. So I looked a little bit at LIGO and decided, no, I didn't want to switch because they weren't going to see anything for another couple decades. And indeed, it took them another couple decades until they saw something. So it would have been a curricula to join back then.
Okay.
But
okay.
I know, and now I know some of the characters. Two of the people I worked for then switched from particle physics to LIGO and are working on LIGO. I've worked on LIGO now for 20 years. And so I know a lot of the people who originally joined LIGO from particle physics. And so I'm more familiar with the LIGO technologies than I am with any of the space stuff because I just haven't paid attention.
Okay. Excellent.
So switching gears.
Yeah, but as you switch gear,
one,
Frank, I wanted to give you an update about, we have been about 45 minutes into it. I'm very aware of your time. So, accordingly, you can adjust what you want to cover. So,
okay, I'll adjust.
There's one more question before you go to IceCube.
Sure.
There's a question from another attendees. I heard there are plans to make such LIGOs in the lunar surface, also the moon. Okay, so I don't know if you know anything about it. So
I haven't heard about a plan for the lunar surface.
Okay.
I'm familiar with plans to build a new round of LIGO-like instruments on ground.
Mm-hmm.
And I'm aware of a plan to build a new set in space, but they're literally you can think of them as satellites, 3 satellites being connected by lasers.
Okay.
That's sort of the conceptual drawing that I've seen and that I've heard talk about. There's probably other things that I don't know, but those are sort of the kind of things that I'm aware of.
Okay, great. All right, let's hear about IceCube now. Yep.
So now neutrinos are a very different beast. They're an elementary particle. They're only weakly interacting, meaning their cross-section to interact is very, very, very small. That means they fly through Earth undisturbed, potentially. And so if you want to observe neutrinos, you need to, out of space, you need to build a really, really big detector to have a fighting chance of having any kind of observations. And that's exactly what was done. And in addition, the detection of neutrinos here is indirect, meaning a neutrino interacts with the ice. This is built into the Arctic ice, meaning the ice of the South Pole. The actual counting house that is depicted here is literally sitting at the South Pole.
Mm-hmm.
And at the South Pole, the ice is, if I look at my thing, the ice is about 3 kilometers thick, close to almost 3 kilometers thick. And what they do is they put these phototubes that are about yay big. I've seen one once that's about yay big. And these phototubes are being submerged, if you wish, into the ice by about a kilometer and a half, 1,450 meters, and then on strings that have cables that go all the way to the top and to the counting house. So how do you deploy this? Imagine a few of these phototubes on a string. You then bore a hole into the ice with a hot water drill, effectively. And as you melt the ice, you let these strings sink into the water of the melted ice and lower them down by 1.5 kilometers, somewhere between 1.5 kilometers and 2.5 kilometers. There is 1 kilometer in height, and there is a kilometer square in distance. And so you're instrumenting a cubic kilometer of ice, therefore called ice cube, the experiment. And that cubic kilometer of ice has 5,160 of these optical sensors spaced in space, so that you have imagine a cubic kilometer instrumented about a little more than 5,000 phototubes. Now, when a neutrino goes through the ice, it will interact somewhere in the ice, some of the time. So you have to be lucky that the neutrino interacts. And then when it interacts, it produces either a charged lepton, it produces either a muon, an electron, or a tau, if it has enough energy. And then those charged particles then interact very strongly with the ice and do Cherenkov radiation in the ice. And that Cherenkov radiation, meaning light, is actually detected by the phototubes. So it's neutrino to lepton, meaning electron, muon, or tau, to light, and light propagating through the ice, hitting one of the phototubes. Voila, you see a signal. And I'll show you what this then looks like. This is an actual event display of an actual muon going through the detector. So there was a somewhere here outside the detector, the neutrino turned into a muon, and this muon flew through the detector, and as it flies, it creates Cherenkov light, and that Cherenkov light hits all of these different phototubes. The phototubes are all of the point. The color is the amount of energy that you detect at any one of them, and voila, you have in fact, I was pointing the wrong way. I think the arrow points actually backwards. So the muon comes from this direction. You see a small amount of light cone, and then you can sort of see that the Cherenkov light cone increases, and you see a much larger number of phototubes hit at the end. And so you then follow backwards and say, this way is where this thing came from, the muon came from, therefore the neutrino must also have come from this way. And now let's tell the telescopes to look there. Am I making any sense?
Yep, sure.
And now there are a couple of things that are sort of interesting, because of course you have neutrinos hitting Earth over, I think, 9 orders of magnitude in energy. And so there is an enormous neutrino flux that hits Earth, and they can detect something like 9 orders of magnitude, but there is only the highest energy neutrinos are actually clean enough to be cosmic, meaning these here are from the sun, basically. This is energy, neutrino energy in GeV, and this is number of events, meaning how often you get one. So the vast majority of neutrinos are from the sun, and they die off because the sun has a finite amount of energy that it can support. And we're lucky in a way. It's a natural phenomenon that is lucky enough that all of the really high energy neutrinos that we care about when we're trying to see violent things in the universe, they are the ones who travel over long distances. And the only ones we see at high energy have come from outside the solar system, basically. And and you can then see this here in a graph. This again is flux on the y-axis and energy on the x-axis. The red stuff is light from a satellite, the light spectrum of satellite, and you can see that the light basically disappears for the reasons I gave you earlier. The universe is opaque, so Fermi doesn't see any light above a certain energy, and the neutrinos exist even above that energy, and are an indication that there are virulent phenomena somewhere in the universe that creates neutrinos. And the name of the game of IceCube was first to show and prove that they can see neutrinos at all. And they can see neutrinos that come from outside the solar system, i.e. neutrinos at very high energies, at energies above this cutoff for photons. So that was established by this paper, and this was a paper in Science in 2013. And then they were trying to look at these, point backwards, and tell telescopes and satellites and whatnot to look in the direction where these neutrinos came from. And in 2018, they saw the first and only, so far, as best as I know, a neutrino that could be pointed back to a source that could also be observed in the optical. And so a number of with light, a number of, if you look at this article, I believe this article basically explains how this neutrino pointed back to a known blazar with the name, funny name, TXS 0506 plus 056, and I have no idea what this means. And so this was a known object in the sky, and therefore you could correlate the neutrino with that known object, and that known object had a flare, a temporary outbreak, if you wish, at the time that IceCube saw the neutrino, and that temporary outbreak was observed by satellites and telescopes around the world.
Okay.
And
very interesting.
And that's the kind of thing that they do.
Okay. This question, there's a question here. When we're on the chat, when we're detecting events from such a very, very long distance, it is like we are going back in time, basically. And he thought it was very
Correct.
interesting. Can this be a basis of time travel? That's the question.
Well, the problem is that these things happened a very long time ago in our time axis, and
right.
So there's really not much that you can do. And let me actually make a comment about time travel.
Okay.
The only scientifically, theoretically possible way that you can have time, not even time travel, but you can long distance travel at high velocity. Time travel, I cannot think of any physical process that would ever allow you to go back in time.
Okay.
I don't see how that can work.
Okay.
Because of all kinds of reasons I don't want to get into. In essence, time is not reversible, and there are too many processes that are irreversible. Think of it, when an egg falls on the floor, it splatters all over. You can't put that egg back together and go backwards in time. The idea that that thing goes backwards, comes back together, Humpty Dumpty comes back together again, that it's not possible for reasons of entropy. It's a statistical impossibility in a funny way, at least in my mind.
Okay.
However, what you can do in principle, you could do space travel above the speed of light by tunneling through curves in space-time. I talked about space-time in principle could be curved. So people have hypothesized that space-time, that there are more dimensions than 4, meaning 3-dimensional space and the dimension of time.
Right.
And that in the 5th dimension, space that we know as something that is Cartesian, more or less, or at least Minkowski or something, and that such space could be in higher dimensions curved, and that we live on a surface in a high dimensional space. And if that was true, then you could tunnel through the 5th or 6th or 7th dimension and connect points via so-called wormholes that would then allow you to do very high-speed travel in certain places where you happen to have such a natural phenomenon that connects things that are out of direct connection in normal space. And this is, if you've seen Interstellar, the movie.
Right. I love that movie, Interstellar. It was a great movie.
this guy who's the Nobel laureate here, Kip Thorne, what he's done in the last decade is not LIGO. He was one of the regional LIGO idea inventors. He's a theoretical physicist, but in the last decade or so, he's actually done Interstellar. He was if you look into the credits of the movie Interstellar, you will find that Kip Thorne is actually credited as I forget what he called him, the technical advisor or something. So he's basically, given that he's at Caltech, and that's where the movie industry is in Los Angeles, he's actually worked in the movie industry of sorts and all kinds of other things in the last decade.
So the physics has a life also in the Hollywood, and that's I didn't realize before.
Yep. At least for Kip Thorne, there is a.
Okay.
He's been in the movie Interstellar was a project of his heart, so to speak.
Wow, interesting.
And
That's an interesting connection. Okay. So we're about at the 1 hour mark. I wanted to again, give you a heads up on the time. So we can go for a little bit longer if you want to cover some.
Let me just let me say a couple more things.
Okay.
IceCube has a plan to run for 20 more years, do a large scale upgrade of its detector. And then I want to make at least one comment, and that is, why do I know about these things and why do I work with these things? I work with these things for my cyber infrastructure leg. My own experiment is another third big type of experiment, the Large Hadron Collider, which I took out because there isn't enough time. And I'm sort of geeking out on these other two experiments, I have to admit. And all of these large experiments have one thing, all of these big science experiments have in common that they're so costly, so intensely technical, they require global investments of human capital and finances to actually make them work. So my own collaboration at the Large Hadron Collider is a collaboration of 2,000 physicists and then another 1,000 engineers across 200 institutions in 42 countries, including India. And so LIGO is 1,200 scientists from 100 institutions in 18 countries. All of these really, really big science experiments have in common that they're really global endeavors. And what that means is that the computing is equally global. What I'm showing you here is the pie chart of the computing for LIGO and the pie chart of the computing for IceCube. Every pie is a computing center somewhere in the world. And you can see that no one pie contributes a really large piece. And so what I do for a living in my computing arm is I build globally distributed computing systems. I do it for computer clusters. I do it for data. We are right now running a content delivery network, in essence, across the world that has caches in Europe, a cache in Asia, in Korea, and a cache in Australia, and a bunch of caches in the US. And so in order to allow for all of these computing centers, all of these computer centers of LIGO in particular, the world over, given that LIGO is such a global experiment, to access data from LIGO, data from Virgo via this infrastructure. And that's what I do for a living, basically, in my non-domain science part.
I see.
And my conclusion is that humanity has built extraordinary instruments by pooling human and financial resources globally. And when you do this and have, therefore, a global collaborations with people from all over the globe that work together for a common cause to build and operate these instruments, then the computing for these logically is as distributed as the collaborations themselves, because people like to build, given that they have to do the instruments in a physical location, they at least want to do the computing in their home countries.
Correct. So
because
to access the data.
Governments like to spend money in their own country and don't just like to write checks that they send to the US.
Okay, right,
or
of
to
course.
Geneva, Switzerland.
Right.
And so this then has created an entire field for globally distributed computing, and that's what I do for cyber infrastructure.
Okay.
And that's it for me for today.
Great. Frank, I'm going to connect a couple of things here. So to basically all the instrumentation, LIGO, IceCube that you talked about, is that they actually generate a lot of data. That's the thing, that data, even for the gravitational wave, you have to process it through a computing system. And the amount of data generated is so much that you cannot have it like a single laptop or whatever to determine or calculate. That's one thing. So you need to have a distributed computing system across the world so that that can be actually, the data can be harnessed basically to be able to understand and find the science that you are actually looking for. Is that a fair assessment of what I said?
And to give you a sense of scale, the experiment that I do at the Large Hadron Collider, we are right now preparing to produce, starting to have a new upgrade of the instrument, and that new instrument and that new accelerator will produce, just for our experiment, about 600 and some more than 600 petabytes of data a year.
600 petabytes.
So within
data.
2 petabytes of data a year. So within 2 years, we will produce an exabyte that is 1,000 petabytes, that is 1,000,000 terabytes, that is 1 billion gigabytes.
Okay.
That's
right. That's the amount of data we produce
every 2 years.
I mean, that's a phenomenal, interesting problem in itself to be able to process. But I have essentially sort of a concluding question for you, Frank. I mean, how would somebody who's interested in this kind of work, young physicist, how can somebody like a young physicist be interested and get involved with something like this sort of activities? Do you have any thoughts or suggestion or guidance for, budding scientists, sort of? How would you characterize?
Yeah, I can describe. Why don't I describe how this worked for me?
Okay, good, very good.
And
okay.
So I was born and raised in a small village outside of Heidelberg, Germany. I went to Heidelberg to get my undergrad education.
Okay.
I then went from Heidelberg to Cornell University for a year as an exchange student, and got stuck in the US and have worked in the US ever since. As a grad student, I worked on design of silicon detectors. Basically, I did VLSI as a grad student for particle physics experiments. As a postdoc, I did FPGA programming for a particle physics experiment. And as a faculty, I ended up being working on globally distributed computing and software for it. So in a funny way, my path has gone up the stack in software and computing, and a lot of this is just one career trajectory. In these large collaborations, you need anything and everything.
Okay.
In my experiment at CMS, we have mechanical engineers, electrical engineers. There are people who are device specialists, material scientists. There are all kinds of different things that are required to make this work. And the way that you get involved is, I think that you pick yourself an institution that is involved in this sort of thing.
Okay.
In India, the obvious places is the largest place in my experiment is probably the Tata Institute. Okay, but there's also places, what's it called? In Pune is a science and technology university.
Yeah.
No, I forget. No, it's not Ayuka. There's another institution. I can't remember now. The nicer or something like this. I've forgotten. There is actually a university in Pune that is a collaborator. I know the faculty there because I worked with her and I visited at her institution, but I can't remember the name right now. Another institution that I know is involved because I know the people there is in Bengal, in Calcutta. The Institute for Nuclear Physics. I forgot the exact name. There's an Institute for Nuclear Physics in Calcutta that is involved in my experiment, and so there's probably half a dozen others where I don't know the people. Okay. But there is one in the south, and I can't remember where. But basically, where I know people personally is in Pune, in Calcutta, and in the Tata Institute in Bombay, Mumbai. And those are the obvious places. And if you Google CMS India, you will find others. If you Google LIGO India, you find institutions that do this sort of thing. And then you get your PhD there, work in that institute, or you get your bachelor's at an institution like that, or a PhD there. Then you typically, it requires they send you to CERN for some period of time in most cases, and voila, you build a career in it.
Very good, excellent. Frank, thank you so much for your time. I think this was a very enlightening talk in terms of what you covered and how from gravitational wave to ice cube that you talked about, and how the human endeavor to try to find those small things, the beauties of what the universe is made of is so interesting, and for that what sort of instrumentation we need to build and what sort of computing system we need to build. And of course we didn't have time to talk about computer networks to transfer all the data also, but I think there are a lot of interesting things goes on, and I definitely appreciate what you do. And thank you for your time today to talk to a group of people. As I said, it's recorded and it's going to be always available, through YouTube, and for others to watch and listen to it later.
Thank you. Thank you for having me.
Okay. There was one last question, sorry. What do you think about debate about gravitation being particle, not wave?
So the whole discussion about whether something is a wave or a particle is really in many ways a red herring, in that there's from a quantum mechanics perspective, it's both anyway. It manifests in one or the other depending on instrumentation and how you look at it. So for gravitation, there is a particle that mediates it at the most fundamental level. That's at least hypothesized, but the phenomenology of it is such that we actually have not figured it out yet, meaning there is no quantum gravity that is self-consistent and that is actually fully understood as a theoretical framework, so that you could understand the quantization of gravity and therefore the graviton. It's hypothesized. It's hypothesized to be spin 2, I think, if I remember correctly, but I don't quote me on that. But we don't have an actual theory of quantum gravity. We haven't understood the phenomenology of this, maybe in part because we don't have appropriate experiments to push that frontier. And one of the hopes is that LIGO might actually, at some point, make observations, or some gravitational wave observatory might at some point make observations that shed some light and pushes theory further in the direction to then allow us to understand what quantum gravity should really be like. But at this point in time, there is no generally successful predictive quantum gravity theory.
Okay, great. All right. Thank you very much, Frank. Thank you for your time, and appreciate it very much.
Thank you.
Okay. All right. Bye-bye.
Bye-bye.